welcome everyone. Hopefully this will be a very enlightening afternoon around the topic of innovation in the energy industry and how we need that innovation to transform the energy system we live with today. My name is Tim Woodward. I'm one of the managing directors at Nth Power. And, as many know, Nth Power has been an active investor in this sector for the last 12 years. We're delighted to host this event. The genesis came from our sponsorship of the Massachusetts MIT's Energy Initiative, the MIGHTY program, which Professor Moniz directs out at MIT. And we've been a sponsor there for several years. And the thought was to bring Professor Moniz out to the West Coast to introduce the activities at MIT to the community out here and a lot of the interesting work that's going on there. And we thought it'd be very interesting to bring together the three leading universities doing research in this area to talk about their programs and common areas of interest. And graciously, Stanford and UC Berkeley agreed to participate in this panel. Let me just go through a couple quick thank yous before I turn this over to Dan Reicher, who will make an introduction of our guest speaker. First of all, Google has been a very kind host. Great facility we're in, great view. We'll have the reception afterwards back in the cafe. They're very active in helping us organize, market, and sponsor the event. Dan Reicher, who many of you know, led that charge, as well as Charles and Aya, who are probably out in the audience. Thank you both very much. Secondly, Brian Walsh was really the inspiration and all the perspiration behind getting this event off the ground. Brian's with Nth Power. He was an MIT alum who's kept us engaged with his alma mater in an active way, and he led the charge in pulling this all together. So right now, let me just turn it over to Dan Reicher, who's going to make an introduction of our guest speaker who's sitting by in the Google offices in Washington, D.C. Dan.
Thank you, Tim, and good afternoon to all of you. Let me also, many Google colleagues to thank, but I'm just going to thank the same two who Tim thanked, Aya Kuma and Charles Barron. Done a great job of putting this together. Welcome to our colleagues from several universities and from Nth Power. To kick things off, it is now my great pleasure to introduce Dr. Kristina M. Johnson, a friend and colleague who has one of the great titles in Washington when it comes to energy. Christina is the Undersecretary of Energy for Energy at the Department of Energy. With that title comes a great energy, having served as provost at Johns Hopkins, dean of the Pratt School of Engineering at Duke, and professor at the University of Colorado. Kristina is a Fulbright scholar, has 142 refereed papers and proceedings, and holds 45 U.S. patents and patents pending in areas like liquid crystal on silicon microdisplays, pattern recognition systems for cancer pre-screening, HD TV and 3D projection displays, and other areas like tunable optical filters, microscope autofocus systems, and of course, to keep things really ticking and be green, rechargeable pacemakers. Kristina, I really like that, rechargeable pacemakers. Kristina, in one sense, comes home today, having received her BS, MS, and PhD in electrical engineering from Stanford. I told Kristina about today's event, and without a moment's hesitation, she agreed to speak. Thanks to the wonders of video conferencing, on which Kristina probably holds some patent, she comes to us from the Google office in Washington, D.C. It is my great pleasure to give you Undersecretary of Energy, Kristina Johnson.
Thanks very much, Dan, and I'm so pleased to be part of this very prestigious panel. And also to say hello to Google Mountain View. I was out earlier this month when Secretary Chu announced the first awards with the ARPA-E competition, so it's a pleasure to see you all again, if not from a distance. Wanted to participate for a couple reasons. One is that as a third-generation electrical engineer, I watched my father and grandfather spend all their life really focused on making their communities better through energy, and it's this time that I get the opportunity to serve in a similar capacity, and it's both a privilege and an honor. And I know that there's a former undersecretary on the panel and also assistant secretary, so it's a pleasure to be with you and talk about the future of our energy. I'm keenly aware of that in order to be successful, we've got to learn how to rapidly transition technology from the laboratory to the marketplace. And so I wanted to talk a little bit about some of the opportunities that DOE is supporting in that regard. But first, let me start by saying that Secretary Chu's made it clear to all of us that from the beginning, science, engineering, and technology will be the drivers for our efforts to help President Obama and the administration achieve the three top priorities in energy. And the first one, of course, is climate. The President set a goal of 83% reduction in greenhouse gas emissions by 2050. And to think about the enormity of that particular task, our energy mix today is about 85% carbon-based and about 15% non-carbon. So that's on the energy side. Of course, it's a little greater for electricity. If we're going to get to, say, let's say we want to get to 42% of reduction in greenhouse gas emissions by 2030, then we would have to take that mix from 85-15 to about 50-50 carbon, non-carbon. And then to migrate out to 2050 to the 83% reduction, we will need to flip the mix to be about 10% carbon-based and 90% non-carbon. And I will include in that carbon capture and sequestration. So we are working very hard within the energy offices in the Department of Energy to put together an integrated strategic plan by which we can take all the different technologies, whether it's nuclear, fossil, energy efficiency, renewable energy, nuclear together, and the smart grid, and to integrate all these technologies in order to hit these goals of migrating from 85% carbon-based to 15% over the next 4 decades. So with that plan, one of the things that we've observed is, first of all, we need a diversity of the technologies. There is, as people talk about, no silver bullet. Even within a sector, there is no silver bullet. If you take fossil fuel, for example, we'll need gas-fired with carbon capture as well as coal-fired with carbon capture plants. So that's sort of the first takeaway. The second major goal is energy security. And I think what we've learned by studying how to integrate all these technologies is that the hardest thing for us to do will be to reduce carbon emissions in transport. And part of that is because we've thrived over the last century on a carbon gasoline economy, and it's become something where we're used to having a car and go anywhere, any place, anytime, and we're going to have to see how to migrate to a less carbon intensive transportation sector. So some of the things that we're looking at are how do we reduce our dependence on oil when we import 2/3 of the roughly 20 million barrels of oil we consume every day. And that's the toughest thing for us to get to, is how do we decrease that? And again, that's going to be a combination of technologies, and also frankly, it's making the internal combustion engine more efficient. It's changing our driving habits to be more efficient. It's going to be electrifying a good segment of the fleet, and all that's going to take time. So my goal as Undersecretary is to put us on a glide path to hitting our targets at 2030 and 2050. And the last is the economy. Secretary Chu's talked about the clean energy as being the industrial revolution of our time. And there's two things we're going to have to do in order to prepare for that. The first is invest in our infrastructure. You know, if you look at some of the statistics, we are still #1 in the world in terms of college graduates per capita. But if we look at the 25 to say 30-something demographic, we're not even in the top 10. Of the 18% of the students that took only 18% of the students who took a science and math proficiency test in high school passed, and only 1% excelled. Only 16% of the graduates going to college today are studying math, science, technology, and only 6% in engineering. So those of you at Google, I appreciate everything that you all have done, and also at the universities, the 3 great universities represented here, to try and get more students into science, technology, and engineering. But this all comes at a time when it's estimated that between 40 and 60% of our energy workforce will retire over the next 5 years. So we're really hitting kind of a perfect storm, if you will. And I think that's something that we're all very concerned about in the future. And the second is our domestic manufacturing supply chain. We don't even have a large foundry in North America. in order to build pressure vessels for nuclear or to build the castings for large hydro systems. So these are our 3 goals, but those are also some of the constraints. So just to summarize, I think the 3 major constraints facing us in order to prepare the workforce, revitalize our domestic manufacturing supply chain, and hit the 3 goals of the president will include funding. You know, right now the science and engineering and technology budget in the Department of Energy is somewhere between $6 and $8 billion. That's just about enough to build 1 power plant and isn't quite enough to have built the Hadron Super Collider. So clearly we're not going to win in terms of a deployment strategy. We have to learn how to do, with the funds we have, research development, demonstration, deployment smarter. There's also an urgency. This is the first time in my lifetime that research and development has to be done under time constraints. So we have a funding constraint, but we also have an urgency of a time constraint. We either put ourselves on a glide path to meet these goals in the next 20 years, or else we will see, according to experts in the climate area, catastrophic changes in our climate. And finally, it's a matter of scale. How do we scale the workforce and manufacturing base to prepare us for meeting these particular challenges? So I wanted to raise the 3 goals and the 3 constraints, and then just talk briefly about the funding constraint. So we were fortunate enough to receive $36.7 billion in stimulus funding, and we've worked very hard to deploy this in some of the highest peer review and strategic way. But we know that that's not going to last. The president has called for spending $15 billion a year on clean energy R&D. China spends $12 million an hour, about $110 billion per year. So we're hoping that as we go forward, in order to prepare the country for this new industrial revolution, that we will indeed see the kind of funding that we need in order to prepare the U.S. to be ready for this new industry. And I'll say a few words about the new industry, but I know there's somebody who knows a lot more about this on the panel, Dan Kammen. But I will say that if you think about jobs per megawatt, the industries we're talking about will generate somewhere between 2 and 10 direct jobs per megawatt. And if you look at flipping the mix from, say, in electricity alone, 70-30, where 70% is carbon-based and 30% is non-carbon, to 30% being carbon-based and 70% being non-carbon-based, that's going to generate something like 360 gigawatts over the next 20 years. With that 2 to 10 jobs per megawatt means that we're looking at upwards of anywhere from 1 million to, say, 4 million new jobs in the clean energy sector. So this is quite a tremendous opportunity that we need to prepare for. We can't do it alone. Our budget isn't that much, nor do I think the government should do it alone. We should support those areas that are way too risky for VCs or other private investment to take on. The question is, you know, and I would pose this to the group, where can we make the biggest impact? Certainly in research, certainly in development, in demonstration to reduce the risk of investment when limited deployment, I think are some of the important things that we need to look at. I mentioned earlier the role of universities is critical in the R&D, and we're looking at a number of ways to work with academics and the academic enterprise. In particular, I think that we need to do more in the energy offices to engage the excellent mind share of the universities, and so we're looking to increase the amount of funding from the energy areas into the university. And lastly, we also need to walk the walk as a federal government. Last month, the president signed into an executive order expanding legislation mandating federal reduction in environmental requirements at federal agencies and facilities. And this executive order was followed up with the Green Government Challenge, and we intend to be at the forefront of leading in energy efficiency. So let me just conclude that I think that what we've learned so far is that we need a diverse portfolio of energy technologies to be successful in attaining the president's 3 goals. And only by looking at where are the gaps in that pipeline from fundamental research to commercial deployment and provide funding there to mitigate the risk for future investment by industry, I think we'll be successful. And I'm certainly looking forward to hearing and seeing the panel's thoughts on how the federal government can better do our job with the resources that we have, and appreciate being part of this panel. So thank you very much.
Thank you, Christina. Certainly for all of us, it's great to have a partner in the administration and DOE that really supports the task at hand that we have. So thanks for your time and comments today.
Thank you.
So let me take a few minutes to frame the discussion. And Charles, there's the two graphs. Sorry, Christina.
Yes. Yes.
You have disappeared. You can stay and listen if you'd like. So the two graphs, which are supposed to show up here, are going to be familiar to anyone who's spent time in the energy industry. You'd think Google would get the technology right. So while they are appearing, the first chart will show the energy supply side of the equation in the U.S. and how we've evolved our energy system from one predominantly based on biomass to what is today, as Christina pointed out, 85% dependent upon fossil fuels, carbon-based fuels. The other slide will show the uses of energy, and it will show how certain sectors dominate our energy consumption. But most importantly, what it shows is that we have a very, very inefficient energy system here in the United States and globally for that matter, but particularly in the United States. Only 42% of the energy that enters the equation actually is put to productive use. 58% is wasted. That's just something that is not sustainable long term. And that's really what we're talking about here when we focus on the need for innovation and transforming our energy system. We need to transform it from predominantly based on fossil fuels into one that is efficient, secure, and sustainable for generations to come. As long-term investors in this sector, one of the biases we carry is that the consumer of energy really doesn't want to change their behavior too much. We've gotten addicted to a system that provides us a lot of benefits for very little cost. And if we are to change the equation, we need to understand what the consumer receives today and what their expectations are going forward. We really become addicted to a system that provides us what I will call low out-of-pocket costs for energy. We don't pay for the direct subsidies. We don't pay for all the externalities. And until we politically are willing to price those into the products, we have an energy system that has to deliver at today's market price and to a consumer who's somewhat reluctant to change. We have a system that's readily available. We have fuels available, gasoline available at every major intersection. We go home, the lights go on most of the time. Didn't for me this weekend, but they go on most of the time. We have become accustomed to a system that we depend on. Google depends on 24/7 absolutely available power, and that's going to be more and more important as the economy grows and the amount of the digital economy grows and data centers, which are the largest load growth in the system, continue to populate. We also have an energy system, a transportation system that's been built for 80 years on the premise of fundamental consumer convenience. That's not necessarily going to happen immediately if we change to electric vehicles. We have very liquid markets, and by that I don't mean physical liquidity, I mean economic liquidity. These are large markets. They're usually not manipulable. Usually local events cannot catastrophically disrupt the markets. We need to continue to diversify our supplies so that we are not dependent on Middle East oil nor batteries from China. We also need markets that are very interconnected so that local disruptions will not create a catastrophic event. In sum, today we have an energy system that gives us energy in just about any form we want to use it, at any time we want to use it, and we don't spend a lot of money to achieve that. But that is not really sustainable going forward because that's the last 100 years, and we need to look at what is addressable for the next 100 years. And what's fortunate is today we face an opportunity with an abundance of natural gas that's been discovered in the last 5 to 10 years to have a bridging technology to get us to that long-term solution. But we need to begin the innovation process right away. These are very, very large markets. It's going to require lots of time, lots of capital to get to the solutions that Kristina talked about. We have in front of us leaders of university organizations that drive innovation and have historically driven innovation for the last 30 to 40 years in the economy we live in today. We're fortunate that they're here to talk about what they're doing in the way of energy innovation. Very exciting work, and they're very engaged in finding the solutions that we all need. One of the things we'd like to have come out of this is a little bit of a dialogue, because many of you in the audience, whether you're entrepreneurs, representatives of the incumbent energy, VCs, I think you need to be interacting with the universities that are leading the innovation charge, because through that conversation, we're likely to get to the right solutions, and we're likely to get them into the market more rapidly and more successfully. So let me turn it over now to the panel. What we'll have is each representative will get up and talk a little bit about their program, and then we'll go through a series of moderated Q&A. I don't know what's happened exactly in terms of questions from the audience, but we've asked that if there are questions, you write them on a piece of paper. They'll be picked up, and we'll sort of try and go through those and consolidate towards the end 15 minutes of audience Q&A. Okay? So Ernie, since you're our guest of honor, would you please come up and talk a little bit about the MIGHTY program?
We didn't get a vote on that.
Okay, well, thanks, Tim, and we appreciate both you and Google hosting this event. I think getting together with Stanford and Berkeley really is a terrific opportunity. Indeed, I think we need to really heighten our levels of collaboration. These are really three terrific university programs in energy. The themes today, they're kind of two intertwined themes. One is, I think, the broad discussion about innovation and the transformation of the global energy system that is driven by a number of factors, but most especially the climate challenge, which, as you heard Kristina's characterization of the energy industry, going to a low carbon system that starts out at 85% carbon is not exactly a trivial task. And the second theme is in our university programs and how these intersect. I think I'd start by providing a reference frame of kind of a characterization of the energy industry. It's I think my colleagues will agree, but if not, they'll have a chance. Because I think it is important to put innovation in this business in the context of a multi-trillion-dollar, very highly capitalized commodity business, highly refined supply chains, very developed customer relationships, supplying essential services to everything we do in society, thereby inviting and receiving strong regulation, considerable political interest, that's a kind of a euphemism, and a system that therefore, for good reason, frankly, has valued reliability and low cost over innovation. And now that is the system that in the climate context, we now face the task of trying to have a major transformation to low carbon in a time scale much shorter than historical time periods for evolution of that system. I mean, we need serious change in a 10, 20, 30-year time period and not the characteristic 50 or even longer time period in the past. So that's the challenge. I would then suggest that to meet that challenge, technology innovation is necessary, but so is policy innovation, and so is business model innovation. My own scoring of that is I'm pretty optimistic on technology innovation. I think business model innovation will follow once the rules of the road get straight. Policy innovation, well, we can argue about that as the follower. In that context, I think I would then discuss what I consider to be key characteristics of university programs, certainly the program at MIT, and I believe at those of our colleagues. One is that we need to involve the entire campus to address technology and policy and business model innovation. It's about science and engineering and architecture and planning and management and humanities, I mean economics and political science, etc. Secondly, I think that our charge clearly involves research, and here again, I think the climate challenge is kind of an overarching theme in terms of how our programs are put together. But those programs must involve both innovation around today's technologies, coal, nuclear, etc., as well as, of course, a real focus on some of the transformational technologies that would, in fact, have a completely new kind of energy system in the years and decades ahead. And at MIT, I would say that, if anything, our flagship program is around solar energy and associated storage questions, but again, focusing as well on innovations around today's systems, plus policy, planning, ... Secondly, of course, we're universities. Education is key, and I would say that at MIT, at least, one of our milestones this year has been the establishment of a novel minor degree program in which all undergraduates can supplement their disciplinary degree with one in energy that includes, once again, science, technology, social science. Third, the universities become hotbeds of walking the talk. So the students get tremendously involved in research and efficiency projects. At MIT, this is having a material impact. We consider to ourselves to be a target-rich environment for energy efficiency, and the students are addressing this quite happily. I might say Nth Power, as a sponsor, has sponsored undergraduate research in energy efficiency projects. And finally, outreach. And in our case, that's been a major focus on outreach to policymakers with integrative technology and policy studies carried out by large multidisciplinary faculty teams. We have published significant integrative reports on the future of nuclear power and of coal. And for those of you waiting with bated breath, nuclear fuel cycle shortly, natural gas and solar energy next year, and the future of the electric grid we expect in about 2 years. Another characteristic that's very important is we must be attracting really the best researchers on campus to the task. This is, I think, a very important metric of how we're doing. And in our case, very pleased that in a major seed fund program that we've had, literally half the projects have been by faculty who historically have never viewed themselves or had been viewed by us as engaged in energy research. That, plus the fact that 15 out of the new 50 faculty hired last year at MIT across the entire campus were doing energy-related research, I think holds great hope for a sustained emphasis in this area. Another characteristic I think is very important is convening power. Our program is founded on industry support first. I will come to other support, but in industry support. We have a long tradition at MIT, certainly, of working with industry. But in the end, industry is going to be where the solutions lie in terms of this transformation, and that's where we focus. However, it's very important in this convening sense that we're not engaging only the large energy companies, the incumbents who are supporting research, but also what we call affiliate members. Nth Power was our first, actually, with a lot of VCs, the entrepreneurial community, because it's the link of the entrepreneurs to the energy incumbents that we believe is going to be a critical part of the solution to the challenges that we mentioned earlier. And so that dialogue across the innovation chain, if you like, is critical. I might say that that I'll come back to this perhaps in a bit, but Kristina alluded to new kinds of DOE programs. One of them is called ARPA-E, Advanced Research Projects Agency-Energy. And there, we were very pleased that there were 5 out of 37 awards last month with direct connection to MIT, including 3 spin-out companies of just the last year and a half in our flagship area of solar and storage. And I think this is another important issue that Tim alluded to. We have to be looking at the basic research, but we have to be part of the innovation chain in getting these technologies spun out and into the place where investors take interest, and ultimately, hopefully, many of these will scale up. It's part of creating an innovation cluster, and I think, frankly, around the Boston area and here in the Bay Area, of course, are 2 real central places for this kind of energy technology innovation cluster. Convening power also means reaching out to the political policy establishment, and again, this has happened. We were very pleased in particular late last month to have President Obama come for a visit and sign a vacuum flange great work, which now has LED museum lighting on it, of course. But actually today, we are hosting at MIT a field hearing of the FCC looking at broadband issues for the smart grid. And so I think more and more universities are being seen as a place to go for these kinds of policy events. And finally, well, maybe 2 more points. One point is I think universities very naturally have, again, another key characteristic, international programs. We signed we think, significant agreement with Tsinghua University in China and Cambridge in terms of a low-carbon energy alliance. But I think with Stanford, Berkeley, MIT, and other universities, we are a natural bridge, I think, to these countries who will, of course, be critical in meeting climate change goals. And finally, I'll just say a word, since Kristina asked for it, on the role of government. This year has seen a real transformation in the new administration of the way the Department of Energy is supporting innovation with new kinds of programs, and from our point of view, in particular, supporting innovation in a way that engages universities much more with multi-year commitments pursuing specific technologies. Energy frontier centers, ARPA-E, hubs coming up, et cetera. And I'll just mention, this is maybe for part of our later discussion, that while this has been a great boost and leads to the spin-outs I mentioned earlier, for example, just one example, but the fact is we have to remember a lot of that came from the very novel use of the stimulus package. That goes away. So the question is now, are we going to have the commitment and find the money someplace to ramp that up over this next years and sustain it for 10, 15, 20 years, which is what it's going to take. If that's done, I'm sure that all of our students will take care of their end of the bargain. Thank you.
It's a hard job following Ernie, that's for sure. So I'm Lynn Orr. I'm the director of something called the Precourt Institute for Energy at Stanford University. And if you think in broad terms, our goals are much like those that Ernie described. I think there's a real sort of confluence of interest here. We have, by my latest count, something like 160 faculty members across 22 different departments working in some way in ways that touch energy. And we wanted to make that endeavor be more visible to students, to provide opportunities to work together when it makes sense to do so,
to support that disciplinary base that is absolutely required in order to be a full-service institution working on these kinds of things. So we've created an Energy Institute that is funded partly by endowment for some new faculty positions and some support for students and some opportunity for seed funding kinds of research activities as a way to coalesce this broad effort across the university. Now, the education side, of course, is very important to us as well. There is huge student interest on our campus. And, well, gosh, if you look at the room today, there are a lot of people here. I suspect we've all had our minds focused on energy because of a period of high oil prices. My hope is that we won't forget that, even if the oil price is not quite so high. I'd be willing to bet that it will be higher than it is right now going forward. So in any case, there is huge interest amongst our students in trying to do something that has the potential to change the world. Indeed, we do need to change the world with regard to the mix of energy that we use going forward. That needs to be accessible, secure, economically viable, and sustainable. And so those are very big challenges because these are very big systems worldwide. So what's our piece of this? Well, certainly research is an important part of it, but I think equally important is educating a group of students who will help do everything that needs to be done over the decades to come. Our program involves a series of elements. The biggest of those is something called the Global Climate and Energy Project. Its mandate is to work across the spectrum of research to reduce greenhouse gas emissions associated with energy supply and use. It has a wide-ranging portfolio, order $20 million a year, that attempts to think about energy conversions. So if you think about the energy system, it starts with some primary energy resource. Could be a fossil fuel, could be nuclear, could be the sun, could be wind. And then it converts it into services that we can use. And if you think about that, really, in the end, it converts it to waste heat, all of it. But the idea is to extract as many services as we can along the way, and at the same time reduce the amount of energy we have to put in at the beginning in order to get the services out through the end. So that gives a huge opportunity space to do better than we're doing right now. If you look at the resource side, the really big resource is the sun. And many of the other resources actually flow from the sun, wind, biomass, those kinds of things. So we need to move to a system that in one way or another makes a bigger use of those energy flows and a smaller use of stored energy that's stored in the form of, for example, fossil fuels. So the Global Climate and Energy Project portfolio is, if you look at what's in it, it's the biggest single element is the solar area. That's a rich opportunity space because we can now make structures at very small scale, so-called nanostructured materials, small enough to be able to take advantage of quantum effects to change properties in ways that are useful to capture a bigger fraction of the sunlight, for example, or to make batteries that give higher energy densities. Those kinds of things. So wide-ranging portfolio all the way from solar to some biofuels effort to carbon capture and storage at the other end, lots of electrochemistry along the way. We also have a group called the Precourt Energy Efficiency Center. It's really focused on the idea that we actually know a lot about how to reduce energy use. And I'll just tell a brief story that makes me look sort of stupid, but I was stupid in thinking about it. So I decided to put in a solar PV system at my house, and I sized it based on the utility bills for the last 3 years, which of course made me look at the utility bills for the last 3 years. And when I did, I was appalled at how much electricity we were using. So while I was waiting for the permits, I actually went to work and measured everything I could think of in my house about where the electricity was going. And by the time I was done with that process, I had reduced electricity use in my house by almost 40%. So that it wasn't that I didn't know how to do it. It was getting me to pay attention. So we need to do that as a society, and we need to make it easier for people to use energy more efficiently, to understand how they're using it, and to figure out ways to make that work better. So that's the Energy Efficiency Center does that. We have a very active group on the basic science of materials that works with the incredible new free electron laser coherent light source that we have at the SLAC National Laboratory just up the hill. And we're creating a new center on sustainable energy that will help us really focus on these large-scale issues of how we get from some renewable resource or some low-carbon source all the way through to the markets that allow us to do this in a way that really does penetrate in a big way. As I said, we'll have some new faculty hires. We're working on assembling lots of postdoc support. We'll work across the spectrum of energy science, technology, efficiency, and economics and policy issues. And we'll try to train a cadre of students who can help lead the charge. It's clear that universities are only one part of what needs to happen here, but I'm pretty sure that it's the right thing to do to take the kind of talented students we have at MIT and UC Berkeley and at Stanford and put them to work on truly
someone calling back in, of lots of new energy programs, and Berkeley has been involved in the sort of process of building out programs on basic solar science, basic biofuel, energy storage, efficiency, energy markets, and I'll come to a few of those. But the real exciting lesson here is that students are now driving innovation, driving demand for interesting programs and courses in a way that's really gotten quite breathtaking. When I came to Berkeley and I inherited from now President Science Advisor John Holdren the Energy Gateway class that was it was called Energy 100 at the time. We've always described this class as drinking energy from a fire hose, a huge flow of information in one semester. That course was about 45 students, and it was considered big relative to other universities back then 10 years ago. That course now is almost 300 students. It is truly this kind of gateway energy class on campus, and we literally turn students away and find ways to get them into sort of other routes in. So it's gotten to be this incredible, exciting moment in terms of student interest in activities. In terms of kind of the environment, though, what I like to say about Berkeley is it's really the anti-Las Vegas. You know, what starts in Berkeley doesn't stay there. And I mean that in a whole bunch of ways. There is Nobel Prize-winning research going on at Berkeley in basic solar, in nanosolar, in advanced energy storage, in some of the control technologies for wind turbines, for the smart grid issues. But it's also been a place where faculty and students have engaged in the whole spectrum of from basic lab projects to being really an energy outreach sort of person and engaging in policy. And thankfully, California's been a great policy leader, from the greenhouse gas laws to the earlier really heroic levels of efficiency rules that were put in place by the state. A number of them traced back to a UC Berkeley professor and a Lawrence Berkeley National Laboratory researcher, Art Rosenfeld, so-called father of energy efficiency, who was actually one of the founders of this unit, ERG, on campus, the Energy and Resources Group. He's now one of the California Energy Commissioners. But all of these things really tie together to make this exciting environment where things go on. And that leads me to the next piece of it, and that is that we've had a unique situation in that we have UC Berkeley and Lawrence Berkeley National Laboratory, you know, essentially a good arm, a good throw up the hill from one another. There are huge amounts of faculty who have appointments back and forth. In fact, the current Vice Chancellor for Research, who's here today, Graham Fleming, has both UC Berkeley and Lawrence Berkeley National Lab appointments. And that's meant that this really large cluster, I think actually technically it's the largest cluster of energy researchers anywhere in the world, has got this back and forth relationship between government projects, basic research, outreach, and application. So it's gotten a very sort of dynamic environment. Berkeley faculty, if you sort of, you know, if you ask them to poll themselves, a very large fraction, something like 35% of all faculty will list energy and/or energy environment as one of their primary, if not the primary research area. And it really does span the spectrum, from people like George Lakoff in rhetoric to basic researchers like the current head of Lawrence Berkeley National Lab, Paul Albasatos, a world-leading researcher on nano-solar technologies, to world-leading researchers on topics in energy markets like Severin Borenstein and Michael Hanneman and many others. So it's a place where all of these things are really melding back and forth. It's also a place where focus on energy environmental issues in developing countries, from the work on basic combustion in people's homes and work on cook stoves that Kirk Smith and myself and others do, in terms of innovating on the science and technology of stoves, to understanding the health effects, to a major report issued last week on the health benefits of addressing greenhouse gas issues as part of this overall mixture of things that are taking place. One feature of this is that many of us have served in international groups like the Intergovernmental Panel on Climate Change, and actually currently I chair the policy chapter of the IPCC, the group that does the assessment of science, technology, policy, economics, feeds it into the negotiations around the Kyoto and Copenhagen and other protocols. And part of that story right now is that at Copenhagen, a week and a half from now, I'll be releasing the first results of the policy chapter. The policy chapter will be the first internationally sanctioned report that is going to have a zero carbon scenario as part of the basic landscape. So Christina Johnson mentioned this switch from 85% fossil to 85 fossil and 15 renewables, to essentially switching that. So now we're going to have scenarios that are being played out for national governments to look at that have that whole mix of decarbonization in place. A lot of that's going to require a real close attention, not just to the basic science, but also the policy. And that's really where I think this interaction that Berkeley has in working with state regulators, federal regulators. Right now, obviously, the president's science advisor was the founder of one of my units on campus. But of course, the Secretary of Energy, Steve Chu, was at Stanford and was at Berkeley and LBL. And then the head of this ARPA-E that Ernie mentioned, this Advanced Research Project Agency on Energy, kind of the place to take the big gamble. Maroon Majumdar was a professor in mechanical engineering at Berkeley and also a program leader up at LBL. So it's got this very interesting mix of things going on. One piece of it I do want to highlight, though, is that if you think about where all of the science and technology leads in terms of making a global difference, many of us, we were actually just talking in the session before, have spent an inordinate amount of time in China over the last few months. I've been doing a monthly commute, unfortunately, or maybe fortunately, to Beijing. And at some of these recent events, we have signed what I think are some really powerful new agreements that support what we're seeing with this President Obama dialogue. My own research laboratory, the Renewable and Appropriate Energy Lab at Berkeley, signed an agreement with the national grid company called the State Grid Company of China to jointly model and develop hardware to manage and implement the smart grid. And if there ever was a pair of countries that have tremendous renewable energy resources, but also are today very dependent on traditional coal, it's the US and China. And so in terms of more policy drivers of a clean energy world, if the US and China start to make that the dialogue, which I really do think we're seeing, it changes the equation dramatically, where you can think about very different sorts of agreements. So if I were to highlight some of the programs at Berkeley that are involved in this, and I mentioned one of my home departments, the Energy and Resources Group, I'm also actually in nuclear engineering and in the Goldman School of Policy, because in the energy world, it's too exciting to sort of stay in one spot. We also have this $500 million Energy Bioscience Institute funded by BP. Chris Somerville, a colleague from Stanford who came over to Berkeley, is the director of that. We have an over $100 million project that, again, Vice Chancellor Graham Fleming was involved in setting up, called the Helios program, to look at novel forms of solar, nano solar, trying to do direct charging of batteries and things, and very, very environmentally friendly batteries. We have something called the Energy Program at our business school at Haas that is looking at energy markets. We have exciting programs that link energy and development. The Blum Center for Developing Economies focuses on poverty issues, and so we have a very large program that's got field efforts around the world. I myself have a laboratory and have run it for now 16 years, based in East Africa, based at the University of Nairobi and at the African Academy of Sciences. Also trying to do the same story, doing basic research, but also being a mechanism to deploy. And we see that over and over again in the kinds of programs that have come up. If I were to end with one kind of final part of the equation, it really would be that the types of innovative new students and programs that we're now seeing in energy is not only long since due, but it represents a real mind shift. When I moved to Berkeley now 10 years ago, it really was unusual. It was almost weird if a professor in energy had or was associated with a company. Now it's almost weird if you aren't, in the same way that biotech, for example, went through a real run-up in some public support, private support, and a cycle that for all the problems in the biotech world has really generated waves of innovations, patents, spin-offs, and programs. And we're now starting to see that in the types of graduates. So one of my recent graduates got a PhD with myself, and Paul Alvasatos, now the director of Lawrence Berkeley National Lab, went off and was the key architect on one of these ARPA-E programs, which was successful. It's an energy storage company. It is now feeding back. So we're now seeing my center, the other center I direct on transportation sustainability, now working directly with one of these startup companies to develop the next generation of very, very long-lived batteries to go immediately into electrified vehicles. And that's the kind of a feedback loop that we like to document. We didn't have lots of examples before only a few years ago, where from the laboratory, a student who did not enter university to study energy became a real leader, won one of these ARPA-E grants, and is now feeding back and drawing students in a larger sphere of energy programs. So those types of projects kind of illustrate the range. And I think you've heard a kind of very similar story in terms of growing not only the number of programs, but the types of areas that they do things that are different than in the past. And clearly that energy challenge we've described is going to require those sorts of not only bright minds who are dedicated to energy, but bright people from outside the energy field really flowing in and making this the engine of transformation for hopefully the next century. So thanks very much.
Thank you.
Well, I'm the other Dan. That was Dan Kammen. I'm Dan Reicher. Before I give you some thoughts, I'd like to recognize some other Google colleagues. Bill Weil is here, our green energy czar at Google, one of the great titles at Google. Jacqueline Fuller, our director of advocacy and communication for Google.org. Michael Terrell, our Google energy policy guru. And Jamie Yude, who's done wonderful press work on this event and many others. I had the opportunity to testify a few weeks ago in the Senate Environment Committee on the Kerry Boxer climate bill. There's intense interest on this committee and several others in Congress regarding energy and innovation, particularly what's going on in terms of research development and demonstration to confront climate change successfully. I stressed to the committee that the critical need to address the climate crisis provides us with an unprecedented opportunity to rebuild our energy system with vast economic, security, and environmental benefits. By putting significant limits on carbon emissions and adopting strong complementary energy policies, we can do the many things that I think we seek: create millions of jobs, reduce our dangerous dependence on foreign energy, and protect ourselves from a global climate crisis. At Google, we published a scenario last year called Clean Energy 2030, which outlines one potential path to a clean energy future. In sum, the proposal reduces U.S. CO2 emissions about 50% below the baseline projection by 2030, while creating 9 million new jobs and net savings of $800 billion. At the global level, the International Energy Agency estimates that between 2007 and 2030, the world will need to invest $26.3 trillion in energy infrastructure to meet currently projected demand. As John Doerr at Kleiner Perkins has said, global energy spending could make clean energy technology, the biggest economic opportunity of the 21st century. The ability of our country, the ability of the U.S. to seize this historic opportunity will be influenced to a large extent by actions taken by government to put a significant price on carbon emissions. But a significant price on carbon, while absolutely necessary, will not be sufficient to address the climate problem, and importantly, won't by itself ensure that many of the technologies that can address the problem are invented and deployed here in the U.S. with the massive resulting economic, security, and environmental benefits. There are 4 complementary policies that I want to highlight that will be critical for the U.S. to take advantage of these opportunities. First, as you've heard today, we must significantly increase public funding of research and development of advanced energy technologies. In 1980, 10% of total government R&D was in energy. Today, it is about 2%. The federal stimulus package has certainly provided a shot in the arm for clean energy projects, but as you heard from some of my fellow panelists, there is a serious risk of falling off a serious funding cliff when these investments run out. We were encouraged when President Obama called for investing $15 billion per year over the next decade in clean energy technologies. Our failure to invest becomes glaringly apparent when we realize that barely a fifth of the top 30 manufacturers of wind turbines, solar panels, and advanced batteries are American. In contrast, all 5 of the world's leading internet technology companies are from the U.S., and the internet itself was the product of federally funded R&D work by DARPA in the 1970s. Let me stress that the private sector cannot completely fill the serious gap in energy R&D funding. The high-risk, early-stage research funded by government that has brought us major breakthroughs in biotech, information technology, and energy is generally not the province of venture capital investment or corporate research. Second, we must increase the capital available to deploy these advanced technologies at commercial scale. Moving from a nation that derives 70% of its power from fossil technologies to one based largely on clean energy will require literally trillions of dollars of investment. The challenge is that raising this kind of capital, especially for innovative technologies, is not easy. The problematic step of moving a technology from a small pilot project, often funded by venture capital investment, to full commercial scale projects financed largely by the banks is frequently the point at which many promising energy technologies die. Indeed, we call it the valley of death. At Google, we're major supporters of pending bipartisan Senate legislation led by Senators Bingaman and Murkowski, which would create a federal clean energy deployment administration to provide various types of credit support to drive private investment in valley of death projects. CETA would be an independent administration within DOE with a Senate-confirmed administrator and board of directors. Third, we need to build a smarter and bigger electric grid to better harness energy efficiency and renewable energy. A smarter grid will let us see our energy use, measure it, price it, and manage it to get the most out of every watt. At Google, we're working to advance the smart grid on several fronts. Our engineers have developed a simple, secure, and free software tool called Google Power Meter that gives consumers an easy means to see their home electricity use on their computer or smartphone. And as you heard from Lynn, when you finally understand what your house is using, it's a lot easier to make changes. I didn't really realize every time my gas-fired furnace turned on how much electricity I was using with the 40-year-old electric motor that was running the blower. I thought I knew something about my own home. I obviously didn't. My son loves, my 6-year-old loves putting that bread in the toaster in the morning and watching our base load go from 400 watts to 2,000 watts for a minute and a half as the toast toasts. The light bulb went on for my son when he saw that kind of real-time energy information. At Google, we've also developed and been testing a fleet of plug-in hybrid vehicles that could help stabilize the grid and also provide massive storage capacity for a vastly greater renewable energy generation. And beyond building a smarter grid, we also need to build a bigger transmission grid that will allow us to tap and deliver our nation's clean energy resources. Fourth, we must set national standards to accelerate the uptake of cleaner and more efficient technologies. Congress should adopt both a strong national renewable energy standard and a strong national energy efficiency resource standard. State renewable energy and energy efficiency standards have sparked new industries and created thousands and thousands of jobs. The federal government should also provide strong leadership on the development of rigorous appliance efficiency standards. Let me emphasize that these policies, if adopted and supported, will help us finally put in place what has long been lacking in terms of clean energy innovation, a complete and robust pipeline extending from basic research to applied research to demonstration projects to commercial scale-up to full deployment. At Google, we call this cycle light bulbs to light bulbs, from the initial idea in a scientist's head to full commercial deployment. Each one of these steps is vital to the whole process, and each step, if ignored, can inhibit the whole innovation cycle. To address climate change with new technology, we do need to increase the size, the speed, and the coordination of the entire light bulbs to light bulbs pipeline. A significant price on carbon emissions and the complementary energy policies I've briefly sketched could finally build this pipeline. A quick example is solar thermal power, where early on, DOE-funded demonstration projects helped prove the technology, where today state renewable energy standards are driving demand, and where federal government finance is helping get plants built. In sum, we do know the not-so-secret formula for accelerating clean energy innovation. With equal measures of policy, investment, and will, we can realize its great potential. Thank you very much.
Okay, is this working right here? Well, if we could harvest your enthusiasm, I think we'd go a long ways to solving the problem. It's great to see there's the enthusiasm at the top of these organizations, and clearly within the organization, the student body has it as well. First, maybe start with just sort of a sense of how your programs are allocating resources today between sort of the major sectors of renewables, incumbent resources, transportation, storage. Can you share with us a little bit about how you think about those sectors, how resources are allocated across your programs?
Well, I actually said part of this already, that we have a big renewables focus. In the transportation arena, we have two pieces that involve biofuels and better batteries as a way to think about, and then that requires also thinking about how you generate the electricity if you want to reduce the carbon emissions associated with it. So we have a group that's quite active in the carbon capture and storage area. So we really tried to adopt the portfolio approach. The one thing that we don't have, but some of my colleagues do, is in the area of nuclear engineering, and that's just a result of not replacing faculty members when they retired at a period when there were no new plants being built in the United States, and so that's an area where we don't work, but otherwise we had a quite wide-ranging portfolio.
So I guess I also gave a little bit of it at Berkeley, but we have this very large effort, $500 million on biofuels, which has also spun off some efforts on not only electrified vehicles, plug-ins and pure electrics, but also efforts within a couple of our transportation centers looking at high-speed rail and the land planning issues. In fact, faculty at Berkeley were involved in setting up a law. It's called Senate Bill 375 in California. That's a smart growth bill that now ties land use planning and why is it that we have people who drive from one end of the mall to the other and that kind of thing. So there's a big, that's right, there's a big chunk on transportation, which is about 40% of actually the greenhouse gas emissions in California. We also have efforts, I mentioned this $100 million or a little more now on solar. There's big efforts on carbon capture. There's a Lawrence Berkeley Lab effort, which is about $22 million on CCS. There's a program called PCERC. It's actually the study of the grid. It's sort of integration of electrical engineers and economists and some wayward physicists like myself who are involved in designing a smart grid to take advantage of the lower carbon fossil fuels like gas, natural gas that is, but also to think about the transition. So in terms of research, there's big chunks in many of the areas, but I think that one of the hallmarks is that the energy industry is very much a policy-driven one in a number of ways. And so an example innovation, actually something that we set up initially between myself and the city of Berkeley, was a program now called PACE financing, property assessed clean energy, that allows you to invest in energy efficiency first, solar or wind second, and to do so with no upfront costs. And it's something that came out of an initiative by the mayor of Berkeley, Tom Bates, and myself, that is now in the House version of the climate bill, and is now in 10 different states have set up versions. So there's kind of an example of the financing side that underpins many of these things as well. So really, things really cross spectrum, and we do have a nuclear engineering department as well. It's one of the, with MIT's and a couple others, it's one of the top rated ones in the country. So try to hit really most of the energy areas.
Well, we also have a broad portfolio, but rather than go over them all, let me give a few, maybe some texture on a few of them. I mentioned, we've all mentioned, solar is a major focus area, I would say. But if you now go one level below, many different kinds of activities that are focused on, let's say, cost reduction around today's silicon-based photovoltaic technologies, novel kinds of solar concentrators, cheap stuff to get more sun on the expensive stuff. But then we also have new materials, organic materials, organic semiconductors, for example, biologically self-organized materials for PV and for batteries. Solar thermal, everything from applying the kinds of novel mirror technologies you see in large telescopes to new ways of getting very, very interesting large amounts of energy storage to make it a dispatchable resource. Water splitting, ultimately integrating essentially the electrolysis step with the fundamental solar conversion. If one can do that, one has the dream of distributed generation potentially with all the storage you want in terms of hydrogen and oxygen. And then in addition to that, doing the kinds of integrative studies, I mentioned the future of solar energy is one of these future up studies that we are doing, where we bring together again faculty from 4 different schools to understand how technology and policy interplay, what is in fact the kind of technology of policy space that would stimulate rapid introduction of solar. That's just one kind of drill down in that area. But let me also mention, I'll mention two other issues. One is, very importantly, I think we have a long-standing now, almost 20-year program that has been pretty pioneering in the integration of natural and social systems in looking at global change, the science and policy of global change integrated. That's interesting also in the context. I mentioned one of the criteria that I think universities are very well suited for, international collaboration. With our new agreement with Tsinghua, frankly, this tool is now going to be refined for application in China and will basically become a tool of the Chinese policymaking establishment in looking at carbon policies. And obviously the U.S.-China dialogue, as was mentioned, is critical. And finally, a different kind of direction is that one of our programs, which frankly is my favorite, is a seed fund program where $150K goes to a researcher for kind of an early stage idea. We've now gone through 2 rounds. We've had 250 proposals, funded 54. But what's interesting now is we are in a position to mine these and to see how new communities can be formed across the Institute. One of them, which we didn't anticipate, was the level of interest from the life scientists in coming into energy. And I don't mean just biofuels. I mean other applications of biological sciences. This is at Berkeley, the EBI is an example as well. We're seeing it in our community, a world-class life science community, looking at novel applications of biology and biotechnology. I think these are the kinds of things that happen at a university, looking at these kinds of new opportunities, and some of them are going to be very, very successful.
What is the process at each organization for determining which programs do get funding, which projects get funding? Is the scale of impact taken into consideration? Is commercial feasibility taken into consideration? How do you go about that? Maybe Ernie start.
Okay, well, I think that's probably a little bit different in our different places. In our case, as I said, our lead source of support. It's funny. I'll take two different ends of the spectrum. Our lead source of support is from industry, and with industry, it is not a consortium. It's industry by industry deciding with us which programs they want to support as fitting into their strategic plans and our faculty want to do. Okay? So that in some sense is implicitly the criterion of possible impact. But on the other end of the spectrum, it's very important as well, is the foundation and philanthropic support, where they are choosing areas. And again, and I see my friend Doug Spring there someplace, again, in our flagship solar area, on the one hand, we have large, for example, this maybe that's worth saying, surprising. We have a $10 million a year program from Eni, the Italian oil company, and half that money is for a Solar Frontiers program. But the industry sponsorship tailors programs in a certain way. We've also had substantial philanthropic support to fund high-risk, student-rich programs in solar, and the combination of these is very rich. And as I said earlier, we see now, just in the year and a half, 3 spin-outs coming in these areas. So I think that's kind of the nature of the program.
So I think that you'll get a bit of a similar story in all 3 cases. We also have this issue that faculty and students are like cats. You can't herd them. You can incite, you can induce them and lead them. And so what we tend to have is the model where faculty, either individually or increasingly in groups, go after funding, whether it's from the federal agencies, whether it's foundations. And so really is there's many, many places to go. But I think that the feature that characterizes the projects in the energy area right now are that we're seeing teams, be it student-led, be it faculty-led, be it Lawrence Berkeley National Lab and UC Berkeley faculty, or also efforts through our university-to-university collaborations. There's a number of collaborations with Beida, with Beijing University, with the University of Indonesia, with Cape Town, a number of places where faculty themselves go after programs that are meeting either basic science needs or exciting individual applications, like developing low-cost, lower efficiency but very low-cost solar to be manufactured not just in the United States and China and South Africa, but in many of the emerging developing nations. So in East Africa and Kenya and Ethiopia, there's efforts that have brought in material scientists at Berkeley, at UC Irvine, at UC Merced to work together on developing materials that can be manufactured without clean rooms, very low cost to meet local energy needs. And it turns out, surprising to many people before they started, but there's really basic fundamental lab research involved in that. It's not an applications program. So you see a whole bunch of things, and I guess the one to end on, I'll end with the same kind of one that Ernie started with. There's a program that was run by Tom Khalil, who was a special assistant to our chancellor, who is now the deputy to John Holdren in the Office of Science Technology Policy in DC. And it was called Bears Breaking Boundaries, a kind of a classic university name. And it was really to give out the same kind of grants to either groups of students or students who then roped in faculty on projects that they really saw as critically important. So you get kind of bottom up, but also some big top down things like the project I mentioned, the BP funded one on biofuels. So there's a range.
Yeah, so the story is similar for us. For this year's round of seed funding proposals, much like what Ernie described, those proposals are due tomorrow. So I will have an inbox full of work to do as we try to select the best. For us, a big part of what we do is through the Global Climate and Energy Project. That's actually funded by 4 companies, and there we do international proposal competitions. So we'll pick an area where we think there's a real opportunity, do a call for proposals with some pretty tough bars. The measures we use there are look for high quality science or engineering science, a pathway for impact on greenhouse gas emissions, and something that's step out in the sense that we're really looking for things that have breakthrough potential, not so much the incremental work that follows on something that's been done for a long time in our university or one of the others. So we also have a combination of private philanthropic support and lots of competition for federal funds as well. So a spectrum. I'd echo what Dan said, that nobody tells a faculty member at Stanford or at any of the other institutions represented here what they should work on. But you can challenge them with interesting and exciting problems that really do have impact, and the energy arena is certainly one of those.
Let me just add, Google obviously things a bit different from the universities. The initial motivation at Google was around our own electricity use in the data centers, which is a fairly significant use. And Bill Weil, who I mentioned earlier, among his responsibilities is in fact overseeing those data centers and how we improve their energy efficiency and green up the supply. But more at the core of the energy challenges we have in this country, we've really broadened the work quite substantially. So we've got Google engineers who are getting up every day and actually working on software. I mentioned Google Power Meter, other software opportunities around how, in fact, you would integrate millions of plug-in vehicles into the electricity grid on a hot day in July in California when everybody gets home at 5:30 in the afternoon and plugs in at the same moment. You might have a little bit of problem. And I think software could have something to say about how you manage that kind of charging, and equally importantly, how you could take advantage of that massive storage capacity that we would potentially have in those millions of plug-in vehicles with large batteries, for example, to store wind-generated electricity that tends to blow more at night than during the day. So some interesting software opportunities across a range of areas. And then on the hardware side, we actually have some engineers getting up every day working on some clean energy hardware. For example, like you've heard from others, how would you lower the cost of mirrors for solar thermal, radically lower the cost of those mirrors to really drive down the cost of deploying it. Google Earth, Google Maps, YouTube, lots of things you can do with those. We've done what we could to get the word out, for example, about advanced geothermal technology, so-called enhanced geothermal systems, or EGS. You drill deep enough anywhere around this country or anywhere around the world, and you get to a heat source. It's 365 days, 24 hours a day, and big opportunity. So where are those resources? How do we begin to exploit them? We've made several tens of millions of dollars of investments in clean energy technology companies across a range of technologies, and we'll make a step soon into energy project investing as well. How do we go into those sorts of areas and have some impact as well in getting actual medium and large scale projects built? And finally, certainly last but not least, is the policy arena in Washington in particular. How do we have some impact there? And some focus areas for us have been, number one, this whole Clean Energy Deployment Administration. How do we get that actually adopted by Congress? Number two, how do we actually reach $15 billion a year in clean energy R&D? Increase substantially over what we've been spending in recent years. That's a heavy lift, but it's one I think everyone up here agrees we need to do. And what do we need to do from a policy perspective to make that happen?
So let me just ask a little bit about the pros and cons of private funding versus federal funding. At some level, there's a lack of federal funding, so we've turned to private sources. What issues come with locking up IP, or as folks out there might want to interact with the university in licensing some of these technologies? Are there limitations because of the way you've had to structure your organizations?
Well, I could just say a few words about that. The Global Climate and Energy Project is sponsored by 4 companies, ExxonMobil, Schlumberger, Toyota, and GE. Those companies get a royalty-free license to the patents. Stanford owns the patents. They get a royalty-free license, but we're free to license them elsewhere. And any research that involves graduate students at Stanford must be publishable. There might be a 30 or 60 day delay to get the patent stuff in order, but there's no restriction on publication, and there's freedom to license. And so there is an opportunity to get the technologies out.
So it's actually quite similar at Berkeley, from very small individual grants that might come from individual donors to things coming from the Energy Foundation, kind of classic public foundation supported work, all the way up to the very large, the $500 million one from BP, where the company that funds it, BP, has a right of first review. They get to look at the projects first, but then they go out to be competed if the one doesn't set a deal. So there's a real range, and we have energy projects that are literally go from that few $1,000s for a researcher all the way up, and in a very similar way, the campus and IP office manages that with some very standardized agreements. So I suspect you're going to hear a similar thing that all the universities are saying. They're sort of open for business, subject to those same conditions. That right to publish first by students and faculty, and at a public university like Berkeley, also to serve the public interest first, where the research is publicly done, is sort of the standard deal. The one wrinkle that we have, of course, is there's also linkages, as many universities have, to the national labs. And then there's in those contracts, whether it's at Lawrence Berkeley National Lab, we work very closely with Sandia, with Pacific Northwest National Lab, Argonne, and the National Renewable Energy Lab in Colorado. Those can have government-funded projects, which will look a little different, but it's pretty similar structure across the board.
Same.
So 5 years from now, 10 years from now, how do you measure your success? What are the goals that you have established or your sponsors have established to say we achieved them?
I think it's unfair that I get to answer this first and that the other two guys have a chance to think about this for a while. I mean, I think what all of us would like to do is to have an impact. So that means that you can think about impact in terms of students who flow through our programs and who provide the real leverage for what we do because they make career-long contributions. You can think about impact in terms of research results that spawn more areas for research, that create opportunities for energy conversions and transformations that we can only imagine now, but will find their way into the marketplaces of the future. That we've created an educational system that serves students and faculty members well, that we create a way for them to work together when it makes sense to do so, and that we take the intellectual horsepower that you have at an institution like any of the three that are represented here and apply it to something that really does matter to the whole planet.
So I would say ditto too. I'll add one sort of piece of that, and that there's a truly wonderful book, sort of very high, a 30,000 foot level book called Pasteur's Quadrant, written by Don Stokes, who was formerly at Princeton, and it defines an area which he calls Pasteur's Quadrant, use-inspired basic research. There's lots of important applied research. There's basic research for its own sake, but I think a lot of the energy projects and a lot of the motivation for our students and faculty falls into that. Can I do things that's really fundamental in terms of economics or science or engineering, but that also comes directly into use? So I suspect that most of my colleagues, and myself certainly, would say that if the things I was doing personally on cook stoves or smart grid or life cycle assessment for biofuels or developing very low material intensity solar, if those things didn't find their way into large or niche markets, that I would regard that as a bit of a failure. Even if it was really exciting basic research papers, I really want to see what we're doing make a difference in terms of making this low carbon economy profitable, a quicker transition than it would be otherwise, and one that does become a driver for much of the next century.
Well, I would agree with the comments in terms of science, technology, and human capacity. We'll add one other feature that we take quite seriously, and that is, again, this outreach to the policy world and, frankly, influence in the policy world through hard-nosed, objective, technical analysis leading to policy recommendations. And that is one major component of our program as well.
So Dan, the academics duck the question for accountability. How about Google? How are you accountable at the end of 5 years for what you're doing?
If I had to pick one thing, it's that people actually 5 years from now are measuring energy use in their own lives and understanding it and having what it takes to make very simple changes.
Can I sign up for that?
Absolutely. It's really quite straightforward. The good news is that the technology in many respects is there to kind of give people what they need to make much, much smarter choices and to make the right kinds of decisions about how to improve their own energy use. First and foremost, taking advantage of that low-hanging fruit, which is energy efficiency. And as we know, it's low-hanging fruit that grows back. You know, the incandescent bulb gets replaced by the compact fluorescent, which is getting replaced again by the LED, and who knows what comes next. So that, I think, if we're going to measure performance at Google, it's really making that happen, and giving people the ability to make smart choices. As much as I love solar energy and had one of the first legally connected systems in the state of Maryland when I lived there, I think people are making some dumb decisions to put solar on the roof of a house that basically is quite inefficient. And we're building an industry around that I think is unfortunate. So we need to be doing both. We need to be giving people that information to understand their own energy use and to make smart decisions. At the other end of the spectrum, as Ernie said, I think the other thing I'd like to be measured on is that we've really given Congress and other decision makers in Washington the information they need to make much smarter policy decisions. It's not that hard, I think, to come to the right conclusion around energy from an investment, a policy, and a technology perspective. I think it is indeed a lack of information that's keeping us from making the right choices in Washington. So I think we have a real shot at changing that, and the first test will be, of course, what we can do in terms of climate legislation.
Okay, great. So we had asked at the registration for any questions. I'll read a couple of those, and then we'll open it up to just a couple of quick questions from the audience. I think there may be some microphones floating around, hopefully. Anyway, one of the questions is, what is the single largest obstacle to modernizing our current energy system?
Well, I would say it is the fact that that energy we do not charge as much for energy as it really costs us to use it. That is, we don't reflect the externalities in the costs, and that has led us to make a series of decisions about the energy mix that we now need to change. So if we're going to do a good job of recognizing those costs, that will go a long way toward building for the future.
And I think that, that's certainly the number one for me as well. I mean, it's not just putting the price on carbon, but it's also recognizing impact on biodiversity and water and indigenous communities and a whole variety of things that may not all take the same quantitative metric, but need to be part of that equation. I think the other one that's probably second to me beyond pricing the impact of energy is really that the markets for energy need to reflect the values that we want, not just the ones we inherited. And we need to have markets for energy that reflect these features, not just in the price, but in the degree to which we allow ourselves or push ourselves to buy the cleanest, most sustainable energy first and put the barriers up. And there are examples in California and some other states have versions of this. But if you don't set up the market signals, not only will you buy the wrong thing, but you tell industry that innovating in the areas we want, clean, sustainable, job-creating energy, that's not actually our value. And so it's really that whole chain of reflecting what we want, which we don't do today.
Well, I would add to that, particularly in the context of climate, that on the supply side of the equation, the fact is there is too large a cost premium for low carbon. And that is a very big issue that has to be overcome. In fact, that is the goal of innovation in this space. Getting that premium down will make policy a lot easier to make. Getting that premium down is essential if there is to be a global condominium on addressing the carbon problem.
And I just echo that quickly by saying that a major focus of ours at Google is an initiative we call RE less than C, renewable electricity cheaper than coal. It is indeed a recognition that we are not going to get to where we need to get in deploying renewable energy until it can compete straight up with traditional energy sources. And that's a combination of technology advances, smart policy, and putting the right investment tools in place to make that happen. But that's really what it's going to take in the marketplace if renewables in particular are going to seize the opportunity that many of us hope they will.
Okay, so for about 5-10 minutes here, then we'll break for the reception. Are there folks out there with questions? Is there a microphone? Still one of these? Okay. So
it seems like everyone here probably agrees about a lot of the basics of the problem. What about people and politicians and companies in the South, in the Southeast, that don't seem to really have the same types of renewable resources we have near here, and who also have a lot of vested interest in the current energy system? How do we make that policy compromise? Because it seems for the last 2 years that's been kind of the problem.
So the basic question was, Boston and California have a melding of the minds, but the South and the Southeast might have a different opinion. They don't quite have the resources that we have, and they may have other incumbent resources that are important to them.
So I'll actually have to thankfully disagree, because I think we've seen some interesting examples. Texas is now not only the wind leader in the United States, but Texas is going to be the global leader. So 3 years ago, everyone was championing Germany as this remarkable place of wind. Texas is now likely to surpass that quite soon. And part of that was due not just to a wonderful wind resource, but to policy, as Ernie was saying, where the Public Utilities Commission for Texas decided to authorize and to work on the financing so that there will be a so-called the clean energy superhighway to bring the wind power largely from West Texas and eastern New Mexico, some of the cheapest wind power. In fact, that is wind that is RE less than C today in the environment, to bring that in. Florida was one of the most recent additions to this renewable energy portfolio club, the states that have their own standards to set different levels. And actually, Florida is infecting its neighbors. So I've been down to hearings in Mississippi and Louisiana recently, where they're trying to work on versions of this as well. So they may not have started out with all the glitter that we've seen elsewhere, but there's excellent solar, there's excellent biofuel resources, there's offshore ocean energy, there's the EGS, the deep geothermal that Dan Reicher mentioned. So they may be a little bit later to the party than many, but in some cases, that means that you haven't made some of the policy mistakes. There are some downsides, but I actually think that there's a really remarkable range of resources, and you've got to really build towards that mix.
Let me just add that offshore wind on the East Coast is emerging as something of keen interest, and it literally extends from Maine to South Carolina. You go enough miles offshore where you first can't see the turbines, which will be helpful in sighting them, and where there turns out to be a very vast resource and often a topography on the bottom that allows you to sight these turbines far offshore in relatively shallow waters. And we have a real opportunity, I think, to develop a major resource close to population centers. So adding to what Dan Kammen had to say about those other states, I think there's a great wind resource. I do think there is the opportunity over time in deep geothermal. There are, though, there are constraints, and I think that's what Ernie is about to tell us. we have political constraints in some of these states. We to wean these states off of a very long reliance on coal or make the big transition to carbon capture and sequestration. And there's a strong commitment states as well to get to carbon-free energy.
Well, it's all fine and good, and I agree with what Dan and Dan said, maybe for the longer term, but I think the questioner's perception is certainly has reflected the fact that we have very, very strong regional differences. We have very strong regional differences in cost of electricity, and frankly, our failure, in my view, to accommodate those up front in the policymaking process has really retarded our ability to move forward more effectively. Kristina Johnson mentioned that one member of the panel was an undersecretary and one was assistant secretary. That would be us. And reminded me back in those wonderful days that who could be against our discussions 10, 11 years ago about the great big grid that Dan referred to, the one that would resources, renewable resources on continental scales. Well, it turns out that the parts of the country that already had cheap power didn't think it was such a great idea. And I think until we face the fact that there are horses for courses, different kinds of energy mixes in different parts of the country, no one generously mentioned the Northeast, where we got nothing at all, that we simply have to address the distributional effects before we get into serious climate policy.
High altitude wind. You're great for high altitude.
Well, actually, for New England, frankly, the logical thing would be nuclear power, frankly, but that is not on the horizon.
I've heard an overriding theme today from all of you that policy is going to be a key player in advancing renewable energies. I was curious, I've been seeing feed-in tariff programs popping up around the United States. I was curious your opinion on, the effectiveness as a mechanism over an investment tax credit or production tax credit, and what your opinions were on that.
Okay. So feed-in tariff, for those not totally up on it, this is the idea that you give long-term fixed contracts, so secure contracts for renewable energy, ideally across scale. So anything from a local mom and pop store that wants to put solar on their roof to a big solar farm, say in the desert, or a wind farm or something else, gets a fixed long-term rate. It's been very successful in Europe. There's a federal version that's been introduced once and rejected, and looks like it's coming back, sponsored by a congressman from Washington. California is working on a version too. Feed-in tariffs have so far been arguably the most successful measure. So in many of the seeing their long-term costs rising enough that these may be more cost competitive. And so we'll find out where this emerges. It's certainly one of the many. And as Ernie said, the U.S. is a very diverse energy market. My suspicion is that we're still going to have different policies for different regions. RPS, these quota systems in some states, feed-in tariffs in others, some concessions for big projects. But really all of these are wonderful second-best mechanisms. They're all really key things we need in the transition. But it's that price for carbon over time that we think most people think, I certainly believe, we're going to need that, not in the next couple years, but in the longer term, really to dominate, to even out the playing
field. The mechanism we've used to date, largely in the United States for renewables, has been tax credits. But of course, the peculiar thing about tax credits is you need taxable income to actually use them. And in a down economic time like we're in now, they're not very useful to large players who used to find them quite helpful. So it's caused, people to take a second look at the sort of incentives we could put in place. Thus, I think the rising interest in feed-in tariffs. But to Dan Kammen's point, ultimately we've got to get to a point where these technologies can in fact compete straight up, and I think a price on carbon is a big first step in getting there.
I just add that I also like tariffs in principle, but I think one might temper the great enthusiasm for the success in Europe. It depends what the metric is. If the metric was a bunch of today's technology got put out there, okay, maybe successful. But for example, I thought the German overexuberance was not a particularly good policy in terms of an innovation driver, for example. And today in Spain, it's kind of crashing and burning. So I think the feed-in tariffs are a very good mechanism, but they need more careful design than they've been given. There's also the issue of what is the cost of the feed-in. If it's QF land, it's not so good. Anyway, so good idea, but they have not been always implemented in a very effective way.
Maybe time for one more, two more. Yeah, two more.
So far, the panelists have all talked about emissions reductions, but according to work of people like James Hansen, we're already at dangerous levels of greenhouse gases in the atmosphere. So what can you say about negative emissions, both in policy and technology and research in your places?
I don't know. Well, first of all, that we had a workshop partially supported by someone in the audience who I won't name. If you're looking at the questions of modification, because I'm told today re-engineering wasn't a good word. Capture. So I think there are a variety of ideas that I do believe need serious research today. Some of them are not removal of carbon, but things like sulfate emissions to cool sound to me to be awfully dangerous. Got to be studied a lot more carefully as a possible band-aid. And then there are others in which it's really carbon removal, which seem to violate some law of thermodynamics.
I guess if it's a big if, but if we could actually figure out how to effectively do carbon sequestration, you can not only apply it to fossil fuels, but you could actually apply it to biomass fuels, which are, in a sense, they start out as net neutral, the carbon dioxide taken in by the plant and then released when you burn it. If you could actually capture that CO2 and sequester it, you could in fact lead to a net negative in the atmosphere. I think we're some distance off in terms of figuring out sequestration, but it would be a great addition to applying it to coal and natural gas.
I think the piece of this, given that these technologies are largely not available yet, we don't know how effective they'll be, cost, et cetera, is that we pretty clearly need them in the equation, because we have sort of danced while Rome burned for a long time, in the sense that we have emitted a huge amount of greenhouse gases, and we do not know exactly how quickly we'll be able to deploy these low carbon solutions. So we may need this one either as an insurance policy or even as part of a strategy if we discover the rate of climate change is really affecting us. The problem, of course, is that when you wait till you see it happening all around you, and it's a little late to unmelt those glaciers and things. So it's a really challenging point. No question, though, if we're really going to invest in the level of science and technology around energy issues that we're talking about, this should be part of that portfolio. But the debate is still out as to what fraction of this portfolio should be in these carbon negative options versus on the deployment side. And there's a similar debate around so-called mitigation versus adaptation. How much do we fight off what we can get rid of, what we can avoid doing to the planet, and how much do we start dealing with what the planet's going to become, irrespective to that? So we'll see.
I will actually be brief. So the thermodynamic driving force for taking CO2 out of the air is a lot lower than the thermodynamic driving force for higher concentration sources. So if it's strictly capture, it makes more sense to use a whole bunch of other sources first than the air. Now, some of the things that were mentioned were the sequestration with biofuels, that's a different matter, but it actually uses a higher concentration source for the capture part of it.
Yeah, I just wanted to add two very brief comments. One is Dan raised, I think, very importantly, the issue of adaptation, an area where I think we are woefully underinvesting. But going back to the atmospheric re-engineering, so-called, at least the cheap things like sulfate emissions, we really do need to study the science of that much more carefully. But what I would add to it is we should, in parallel, seriously do the research on the institutional structures that one would need for a world that might contemplate doing that kind of a thing.
You can't let the academics get started on that stuff. So I would say that the one thing that, and actually I'm not disagreeing at all with Ernie, but even if we manage to use the, what would you call it, atmospheric re-engineering schemes, that those don't do, they might influence the warming part of it, but they don't do anything to the pH change in. Yeah, exactly. Yeah. So to word more carefully, it doesn't help the problem with pH reduction in the ocean. So there are pretty good geochemical reasons why we need to work on that. Never mind the climate side.
The spirit of our workshop was to hopefully make people understand the importance of mitigation.
I'm gonna get one here too in a second.
So
Must have been a good question.
thus we go back to our lowest hanging fruit, which is energy efficiency. And I think that's changing the subject, but that's what's there. That's what we know we can do now. Yes.
One last question, Jack.
Hi, this should be a pretty quick question. My question is that there's a general consensus, it seems, that we're woefully underinvesting in energy innovation on a federal level. I think that's shared by all the panelists as well as the undersecretary who joined us earlier. And my question for you is, in terms of federal investment, what is the scale of funding you see as necessary to meet the innovation challenge, perhaps on an annual level? And where do you think that that money should or could come from once the stimulus expires?
Well, let me say that there is a number out there of $15 billion a year for federal investment in clean energy RD&D that President Obama has talked about, and talked about that kind of spending over a decade. And that would be a significant increase over today. There are a couple of options of where it comes from. One is through normal appropriations, which is a very tough way to increase this kind of budget, particularly in the lean times we're facing, and particularly with the deficit that we're staring at, the biggest in history. Obviously, the second source could well be if we actually got to climate legislation and be able to tap the funds that come out of putting a price on carbon. That, I think, is some years off. So I think the issue is, can we, in fact, find this through normal appropriations? I think there's strong reason to do so, but I think it's going to be tough sledding over the next couple of years.
I agree with the comment that the timescales don't work out for the carbon allowances. We don't have time. But I do, and appropriations is the obvious approach, but I do want to emphasize there are other ways of going about it, ways that we used to do not so long ago. For example, Congressman Boucher introduced a very simple idea of a very small line charge on electricity to support, he had in mind a fairly narrow focus to support major RD&D around coal and carbon capture and sequestration. Well, the same idea could be extended to other areas. It's interesting, we used to do that. For example, in natural gas, there was for many years a surcharge on interstate gas transmission, which funded a $200+ million natural gas R&D program run through a nonprofit organization, GRI. That was a casualty of deregulation. But it's interesting, these ideas are coming back. There is an example in place with a piece of the annual oil and gas royalties of the government going towards natural gas supply R&D, There's the voucher idea, which is in the Waxman-Markey bill. And so I think we may be going back to these approaches in which a small charge on energy use is reinvested into RD&D.
And actually, if you look at the success in some other fields, that policy really has some legs. When there was a national debate over essentially doubling the NIH budget, the medical biotech R&D budget, there was a very public debate about doubling it. It happened. It wasn't perfect, but at the same time, private sector investment actually went up, not by factor 2, but by most measures by a factor of 10 to 15. And so, you really want to structure these in ways where the public sector provides the kick to get it started. A friend of mine in DC likens this. He says, well, because we've done it in biotech but not in energy, we may be living long enough to see the error of our ways. But it does kind of highlight there are a bunch of tools out there. We have another mechanism that actually Ireland pioneered. There's a neat thing to do, to have a fee-bate. Essentially, when you buy a vehicle, for example, in the transportation sector, that if you buy one below the standard for that class of vehicle, there's a tax. That goes to people that buy the vehicle that are more efficient. And the Irish liked it so much, they decided to make this a tax that keeps on giving, in the sense that they not only do it when you buy the car, but then every year when you get it relicensed, it's based on this. So they penalize you not once, but they keep penalizing you for your original sin, so to speak. So there are some clever new mechanisms that can go into putting together a portfolio, because you really want to transition this to not being all public sector. You want to have a strong long-term public sector, and I think it's going to be more than a decade. And we're not talking about, in my view, 10 years of 15 billion. Hopefully we're talking a lot longer. But we need to find ways to make this part of our science technology deployment process in the private sector too.
And soon all the cars will be above that. That's right. It's like exactly.
Okay, well, first of all, I'd like to thank Dan Reicher and all the team at Google and the space. This has been wonderful for you to sponsor this. Our panelists, again, if we could harvest that enthusiasm, I think we'd go a long way, and it's great to hear that the universities are so engaged in finding these solutions. We will all gather straight behind us in the Google cafeteria, and I think we're here for an hour or so. So thank you all very much for your time.